Hey everyone, so I just wanted to give a quick micro lecture on some of the average values that we observe on the planet within seasonal variability. So we know that weather is always changing and varies from place to place, right? And if we look at these global averages over long periods of time, it really helps us isolate the kind of semi-permanent state of the atmosphere. This helps reveal persistent patterns and global circulations throughout the atmosphere. So what we're going to do today is look at surface temperature, surface air pressure, upper level winds, and precipitation. So I know we already talked about global circulation, right? And like those three cells, those three global circulation cells, the Hadley, Ferrel, and polar, right? So this may help provide a little bit more basis as to why those winds do what they do. Okay, so first I want to look at the average surface temperature for January. So here's our planet, right? And here is North America, South America is down here. We have Asia, Africa, and Australia. And over here on the left-hand side, you can see that we have, we're looking at January for the Northern Hemisphere. Right, so think to yourself, what season are we in January, and what season is, and we being the Northern Hemisphere, and what season the Southern Hemisphere is in. Southern Hemisphere is in summertime, right? So even though they're in the summertime, Antarctica is still quite chilly. But if we do this comparison for July, we can see a very, very, very different pattern, right? Try to think here where you can observe the coldest temperatures, perhaps, maybe some of the warmest temperatures, even some cool temperatures here. Think about what this particular, we're just north of India here. So think about what exists there and why, on average, that may be cooler than the surrounding much warmer areas. Think about that. So it's the Tibetan Plateau. So it's a higher region, right? And so we're in summertime in the Northern Hemisphere in July, and that is also why the temperatures at the surface are much warmer. So if you compare and contrast, as I kind of toggle back and forth, try and see where you can spot the greatest temperature change, right? Where do you see the starkest difference in temperature? So really overall, we can see that there's really strong temperature gradients that exist, especially in the wintertime in the Northern Hemisphere. It really dips south over land and more north over water, and we call that the polar front. These temperature gradients are less strong in the Southern Hemisphere summer, but are strongest in their wintertime. And the equator is someplace that stays relatively the same. So there's not a whole lot of temperature change. And that makes sense, right? Because the sun angle doesn't really change too much over the equator season to season. And landmass plays a massive role in those temperature gradients. So if you were unable to see some of those patterns, I would suggest taking another look at the slides, which will be posted on iLearn as well, just so you know. So try and see those patterns that exist there. And now I want to move upstairs. So I want to go up to looking at our upper level heights and winds. So remember, when we're looking at upper level maps, we're looking at heights. So that's what these numbers here indicate. And the shading here indicates wind speed in knots. So this is in January, again on average, right? So you can see where these height lines get really, 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 really close together. That indicates an intense gradient, right? Think of like a really, really steep hill. So where that gradient is really intense, notice that that's where the wind speeds are the fastest. Right? And you can even see that over in the North Atlantic as well, and even a bit down in the Southern Hemisphere also. But it's really, really, really strong in the North Pacific in January. And then if we go over to July, once again, a completely different pattern. The jet stream is not nearly as strong in the Northern Hemisphere as it is in January, right? That's a very, very stark difference. But it's also a little bit more kind of straight west to east, if that makes sense. It's a little bit more of a wavy-ish pattern, at least in the upper level heights, right over, you can see this trough right here. And that does not exist as much, nearly as much anyway, in July. And you can also kind of see in the southern hemisphere at least a little bit of a split in the jet stream. And that could be due to landmass interaction there. And if you were to look at a schematic for both hemispheres, this is kind of what you would get. So this is both hemisphere winters. So this top panel here, the northern hemisphere would be for January, and the southern hemisphere would be for July, right, for each winter. And again, you can see a very, very different pattern between the two. So there's these really strong height gradients, again, also correspond with locally long, narrow wind jets, which we call jet streams. You can think of it like a little tube of really fast air movement. They tend to be stronger in the northern hemisphere winter with troughs and ridges that exist. And then in the southern hemisphere, there's this lack of that wavy pattern, right? And the jet is not nearly as strong in both seasons. And there's two sort of semi-permanent jet streams that exist, the polar and the subtropical. So those names are kind of given simply by their location. So polar being near the polar regions and subtropical meaning near the subtropical regions. But why do those jet streams exist? Well, it's oddly enough because partially due to temperature, right? Our equatorial region is in a sense thicker because it's warmer, right? Remember thinking of things being how dense things are. So when you're warm, you're less dense, you're loosey-goosey. When you're cold, you're more dense, you're more compact. So because the equator on average is much warmer than a lot of the planet, especially, in January for the northern hemisphere winter, you get that really, really steep gradient and then in the upper levels, right? So that gradient is a pretty nice little sweet spot around about 40 degrees-ish, 30 to 40 degrees latitude. And in accordance with geostrophic balance, that term again, the stronger gradient then leads to stronger winds. So that's why we see the jet stream, the polar jet stream in that region. Now we're going to move back downstairs, but instead of talking about temperature, we're going to look at surface pressure. So what we have here, this is our average surface pressure for January. Remember, pressure is how much atmosphere you have on top of your head. And it's quite fascinating, really, to see the differences between the northern hemisphere and the southern hemisphere. So why do you think it's so much more muddled in the northern hemisphere than in the southern hemisphere? Just give you a moment to think about that. Maybe even pause the video for a second to kind of have a look here. And the big thing really is the continents, right? It's a much more messy of a pattern in the northern hemisphere than the southern hemisphere, pretty much almost entirely due to the stinking land being in the way. And then July is a very, very different pattern, right? If I toggle back and forth between the two, extremely different patterns between the two seasons. The biggest things are off our coasts of the United States, right? We have two massive highs, one that's in the North Pacific and the other that is in the North Atlantic. And that actually has some climatological impacts on our region. And then notice also here, there's a really, really, really intense high over Antarctica in July. Remember, that is Antarctica's wintertime. The winds are very, very strong there for the most part during that time. And they're actually called katabatic winds. Your book goes into details, but I'm not going to, just for sake of time and for sake of context. But it is a very interesting phenomenon if you have any desire to have a look at that. But I want to focus really quick on on our coasts closer to home, right? So in our summertime, we have this massive high that's parked off of the coast. And this brings northerly winds, so winds from the north. which are generally cooler, whereas the East Coast has winds coming, southerly winds, so they're coming from the south. So this can make for generally cooler summers for us here in California, whereas summertime on the East Coast can tend to be much warmer, right? Think about generally in our summertime, like there's generally Carl the Fog is just like parked off our coast, right? That's one of the reasons for that is because of the massive Pacific high off the coast. So if we were to observe sort of some observations that we can see from those are that there's these subpolar lows that exist between around 60 to 70 degrees north or south, especially in the wintertime. The lows tend to be a bit stronger in the winter. We call them the Aleutian low and the Icelandic low. We also have subtropical highs around 30 degrees north or south. These tend to be stronger in the summer, meaning the Pacific high and the Bermuda Azores high. Actually, I'm going to go back just a few slides just to also show. So one of the reasons that we don't get a whole lot of rain in the summertime here is because of this massive high that's parked off our coast. Whereas in the wintertime, a completely different pattern. And this low here, this counterclockwise motion also allows for storms or any sort of moisture to be funneled onto our coastline. So that's one of the reasons why we have a wetter winter and a drier summer. Speaking of wet and dry, if we were to have a look at the average precipitation around the world, this is in rain rate in millimeters per day. The heavier the darker the color, the darker the rain rate, the heavier the rain rate. So what you can see, and this is for the whole year, by the way, this one is not divided up into seasons, but what you can see is this lovely little belt that exists around the equator of higher precipitation rates per day. Indonesia is also nicely in that, in the Philippines, right? You have the rainforest here as well, and the African rainforest in the Congo, and even a little bit off of the Pacific Northwest coast. You can kind of see some nice higher precipitation rates there. So I want you to think about why that exists there. Perhaps consider reflecting on some of the, going back to the global circulation cells, right? That little part near the equator, there's a specific name for it that exists there, and this showcases that pattern really, really nicely. So I'll have these slides posted on iLearn for you to access at your leisure. Let me know if you have any questions, comments, and or concerns on this part of the section. Thanks so much.